So today we're going to go over Newton's law of universal gravitation. So we're digging further into the concept of gravity. We've spoken about gravity before, but we're going to really dig into a lot more theoretical concepts of gravity. Okay. You're starting to see a connection between what we learned about circular motion and gravity, which we will hit on. So we're gonna need to be able to describe the law of universal gravitation and then use it, because it comes with a formula, like most laws, and then calculate G, which is yes, and then describe the effects that gravity has on objects. So just in general, we're going to be looking at how gravity affects things. So to begin with, for orbiting objects, they orbit the Earth due to the centripetal force of gravity. So when an object like the moon or a satellite is in orbit around the Earth, the centripetal force for that object is gravity, which is the idea of centripetal force is actually how they first started to quantify the idea that gravity must exist. Like, obviously we knew that gravity exists because we throw something up, it falls back down to the Earth, but why, And they started to understand the concept of gravity because of centripetal force. And it was actually Isaac Newton who first came up with it. And he used this idea of launching an object causes it to fall in a parabola, right? So you have your object on the surface of the Earth, you launch it, and it falls in a parabola, right? So they do parabolic motion. We've seen what that looks like. We know what falling objects look like. Well, if the speed of that object is high enough, then the curve of their parabola will actually match the curve of Earth, which means they will be falling at the same rate that the Earth is falling away from them because of the curve of the Earth, and therefore they will just keep falling perpetually then from then on. So I can show you an image of this, and you have it there on your notes already, actually. So you can see the smaller parabola at the top, right, when we don't have the right velocity, and how their curve, they keep curving and curving and hitting the Earth. But when you get one launched fast enough, the curve of the parabola matches the curve of Earth. So it just keeps curving and curving and curving until it comes back to where it originated from. Which is why it requires a great amount of speed to get an object into orbit with Earth, right? Because the Earth it has a very large curve that you have to match with your parabola, which requires a pretty significant speed. But that's how we launch things into orbit, and it's how Newton theorized that we know here on Earth circular motion only continues if you have a force pulling inward. So whatever is holding the moon in place around us must be an inward force, right? And then he theorized that force is what we call gravity.
Okay.
So, pretty cool stuff from Mr. Newton. So he discovered gravity as centripetal force, and he is credited with the discovery of gravity in the first place, at least in coining the idea of it, and that it exists and that it's a force that pulls on things. And so his crowning work was the theory of universal gravitation.
Not the laws?
No. A lot of people know him for his laws of motion because they're a little more well known, but this is one of the most significant discoveries in science, and it was his discovery.
Gotcha. Okay.
So I would say it is his crowning achievement.
Oh,
Yeah. So his theory of universal gravitation says the following things. 1, every particle is attracted to every other particle via gravity. So you said that your bell ringer was a slightly elementary grasp of the concept of gravity, and I would say your definition that gravity is the force that pulls objects to the Earth is not elementary, it is what the general populace believes the definition of gravity is. However, a better definition of gravity is that it's actually the force of attraction between any two objects, whether those objects are the size of the Earth and an apple or the size of two particles.
Oh, yeah.
So, here on Earth, we experience gravity mostly in our relationship with Earth. And that is simply because Earth is enormous. And we'll touch on this a little bit later, but the enormity of Earth means that the force of gravity between us and the Earth is so huge, it makes any other forces of gravity we may be experiencing pretty negligible. So we don't experience effects due to them. But if you and I were in outer space and there was nothing else around, there would be an attraction of gravity between you and I. And we might orbit each other due to that attraction. But here on Earth, the attraction of gravity between you and I is so teeny tiny compared to the attraction between us and Earth that we don't feel it, and we don't feel its effects. So the strength of the attraction between particles can be found using this equation, and you'll notice that it has two masses in it. One of those masses for each object experiencing the attraction. And since mass is involved, that should give you an idea about why the Earth is winning that force battle. Because the Earth's mass is huge compared to anything else on it. So a lot of times you'll see this equation with the M1 subbed for ME, and that would simply mean mass of Earth.
Okay.
So sometimes they'll sub that in because usually when we're using it here on Earth, one of the masses we're discussing is the mass of Earth. So, and fun fact is this equation was actually eventually used to determine the mass of Earth. So when it was written, we didn't know what it was. Now we do. In that equation, Fg is the gravitational force. G is the constant of universal gravitation, which at Newton's time had not been calculated and has now been calculated. 6.673 times 10 to the negative 11, and then the unit on that is newtons times meter squared over kilograms squared, which is a horrific looking unit, but is the unit we are stuck with. Mass 1 and mass 2 are the masses of whatever two objects. Oftentimes mass 1 is subbed mass of Earth. And R is the distance between the two objects, and it's important to note that we start from their centers. So from the center, if we were doing between like the Earth and the Moon, we would measure the distance between their centers, not between their surfaces.
Gotcha. So would you technically measure the diameter and then cut it in half?
You could, or just take the radius and then the distance between the two objects and then the radius. Mm-hmm. Yeah. Now, universal gravitation follows Newton's third law of motion. Makes sense. This guy wrote both of them. But to illustrate this, we'll consider the Earth and the Moon, right? Mm-hmm. The Earth's gravitational force is what keeps the Moon in orbit around the Earth. So the Earth pulls on the Moon with a gravitational force, and the Moon has a gravitational force that pulls on the Earth. And that force is equal to the strength of the Earth's gravitational force, but in the opposite direction, pulling back towards the Moon. So then, why does the Earth not orbit the Moon? Well, it comes back to the fact that the forces are equal in strength, but the two objects have pretty discrepant masses. So the Earth is much more massive than the Moon, which means that the centripetal acceleration will be less because force is equal to mass times acceleration. Acceleration is force divided by mass. So when you divide the force by mass, that's much larger. You get a much smaller acceleration out of it. Okay, and instead of orbiting the Moon, the Earth does still experience some acceleration due to this force, but it's only enough to make it move in a very small circular path around a point that is inside the Earth. So it does move a little bit because of the moon, but not enough for us to see it. It doesn't orbit the moon. For the same reason, when you drop objects on Earth, they accelerate quickly down to the Earth, but the Earth doesn't move the same distance up to meet them. So, when I jump, the Earth pulls on me to come back down, and I simultaneously pull on the Earth with an equal and opposite force, but that force does next to nothing to the Earth's mass, whereas it rapidly moves my mass back downward. So, same basic principle. And like we said earlier, important to note that any two objects can have gravity between them, but here on Earth, the forces of those gravities are pretty negligible compared to the Earth's massive gravitational force. Here is our very first example problem using that lovely universal gravitation law. Okay. So if the sun has a mass of 2.0 times 10 to the 30 kilograms, and its radius is 7.0 times 10 to the 5 kilometers, what mass must be located at the sun's surface for a gravitational force of 470 newtons to exist between the mass and the sun? So I'll just draw a picture to help illustrate what this problem is asking, okay? They're saying we have the sun, we have an object sitting here, okay? Distance from that object to the center is the radius. Mm-hmm. And then there's the mass of the sun and the force that exists between them. So what must be the mass of the second object is what we're solving for here.
Gotcha. So M2.
Yes.
Oh gosh.
So if we take our equation, right, that Fg equals gm1 m2 over radius squared, okay? And we want to isolate m2. We want to get m2 by itself, okay? So the equation we should wind up with, if we manipulate the equation correctly, is m2 is equal to force of gravity times the radius squared divided by the universal gravitational constant and the mass of the sun. Did you come up with a similar equation?
Aha!
Forget a piece?
Since the radius was 10 times the fifth, I saw the exponent. I was like, oh, that's it. Forgetting to do the square. So
Forgot to square that exponent, or square that radius. That'll do it.
So 1.7 times 10 to something?
1.7 is closer. And so then we do 470 times 7.0 times 10 to the 5th kilometers. That's a terrible kilometer. Then the universal gravitational constant, which is that great big 6.673 times 10 to the negative 11, and the great big unit that I'm just not going to write out. And then take that times the mass of the sun, which they gave us, which was 2.0 times 10 to the 30th kilograms. And when you do it, you should just come out with 1.7 kilograms.
Weird.
Yeah. Okay, we're going to go out to the internet. Because this book has been wrong before. Mm-hmm. So... to the 5th. comes up with it. See, they come up with the same one here, but I don't see how, because we're doing the math. This says times 10 to the 8th, not 10 to the 5th.
So maybe a printer error? Because, yeah, down here it says 8.
But then in the problem it doesn't.
It says 5.
We found it, Kayla. I bet that would get us the extra 6 we need.
Mm-hmm.
Yep, there it is. Printing
So
error.
it's a printer error up here, everything else.
Dadgummit, that is the 18th time this book has had an error of some kind in it, and I'm tired
That's
of
like drastically making
being
things problem.
lied to. Well, at least we know we did the problem right now.
Yeah.
Okay, we can move on.
I'm changing it in my notes.
Do it. I will go back and edit that later. And in fact, I'm going to make a mark in the book right now and say, look, there's a little printing error. It's an 8. 8, not a 5.
Which is so funny that it's not through the rest of it, which makes you which shows you that it's not meant to be.
Oh, no, it's not an error. They converted it to meters, which we should have done. Not an error.
Can I go to the bathroom?
Yes.
Just a brain error.
Just a brain error. I didn't realize it was in kilometers. I'm going to make a mark so I don't forget. It goes from 10 to the 5th kilometers, but we needed it in meters for the problem, which would, in fact, change our answer. Okay, so we should be a little less mad at the book, but it's fine.
You did excuse. I'll forgive you.
So in 1798, a man named Henry Cavendish used Newton's law to calculate the mass of the Earth. So he wanted to set up an experiment in order to find the value of G, and then using that value of G, he knew he would be able to calculate the mass of the Earth. So you can see his experiment here, okay? You have the picture on your notes. Basically, you have 2 masses suspended on a lightweight bar, and then there were 2 fixed masses on the ground that were used to attract those smaller masses. Then they used a laser to determine the angle between them and use that information to determine what the gravitational force between them was. The math is beyond the scope of what we're going to do in this class. And then with those masses, the distance between them and the gravitational force known, they were then able to solve for G. Newton's law can also be used to explain high and low tide, which I found to be an interesting concept. So basically, when the moon, when you look at the line that the moon makes with Earth, right? On both sides of the Earth, the side closer to the moon and the side further from the moon, there's a difference between the gravitational force at the Earth's center and the one at its surface. And that causes a bulge of water to form, that difference in gravitational forces. And it's a little bit more complicated than what I can easily explain and what the book could easily explain to you. But all you need to know is that it's a difference in gravitational force that causes that bulge of water to form. And then since there are 2 bulges and the Earth rotates once a day, when points pass through those bulges, they experience a high tide. And when they're parallel to the bulges, then they experience a low tide, and then they go back through a high tide spot. So it's interesting. People often think of the water as coming and going, but what's really happening is you're just like passing through areas of high water and low water.
Gotcha.
So let's talk a little bit about gravitational fields. Okay, Newton didn't know what caused gravity. He just was like, this is a thing, it exists. And since then, we have come up with theories. And the main theory right now is what we would call the field theory, that gravitational fields exist for objects, and that the interaction between a mass and the gravitational field created by another mass is what causes gravity. So basically, the easiest way to think about it is when I lift a ball off the ground, I use kinetic energy to move it. And when that ball is now above the surface of the ground, it has energy, potential energy that's stored. But where are we storing that energy, right? Where does it exist? Well, the field theory suggests that the potential energy is actually stored in the gravitational field. A little conceptual today. Like I said, we're getting into some more conceptual gravity things. So you can describe gravitational fields by their strength, which we abbreviate as G. So G is equal to the magnitude of a force exerted on a unit of mass at that specific point. So we can calculate G as the force of gravity divided by the mass of the object that it's acting on. Because acceleration is equal to force divided by mass, and G is equal to the force of gravity divided by mass, at any point, the value of G is equal to the acceleration due to gravity, which is why your brain was like, G, yes, acceleration due to gravity. We've had that before, right? Well, yes, but we're thinking about it in a different way now. We'll pick up with these on Monday. We'll finish them.